So in this video, we're going to look at two worked examples involving related rates. So recall that in a related rates problem, we have an equation that relates typically two or more variables to each other. And we want to take the derivative of them with respect to time because the relationship has to be maintained, but the values are changing in time. And if we have sort of more than two variables, usually we have to come up with a relationship between the third variable and one of the other two variables, because we have only one in a typical problem, only one of the inputs that are changing, the rate at which it's changing, which will allow us, if there's only two variables, to find the missing rate. But if there's three variables, again, we would need that relationship so that information about one of the remaining variables will give us information about the final one. So in this particular example that we're going to look at first, there are only two variables to start with, and this is sort of a typical related rates problem. We have a ladder. In this case, it's a 25-meter long ladder, which is leaning against a wall. Sometimes it can be helpful to draw a diagram of what's going on. But then we have 25-meter ladder leaning against a wall. And basically, you expect that it's forming a triangle. So like here's our wall and the ground, and here's our ladder, right? And so we have some X distance, the base is away from the wall, and we have some Y distance that the ladder is leaning up against the wall. And we know that this hypotenuse, the length of the ladder, that is not a very convincing 2, is 25 meters. And what the problem is then telling us is that the base of the ladder is now beginning to move away from the wall at a rate of 1 meter per second. So the base here is going this way. And so what we want to do is we want to find out essentially how quickly the top of the ladder is coming down the side of the wall. All right, now, because this is forming a triangle against the wall and the ground, we know that we basically have this relationship where however far it is away from the wall and however far it is up the wall is defined by the Pythagorean theorem. 25 meters is the hypotenuse, that's the length of the ladder. And then the two sides of our right triangle, presumably the wall is straight, then this would make a 90-degree angle. And so the two sides squared equal, when you add them up, to the square of the hypotenuse. Now, one mistake that students can sometimes make is that they may try to like plug values in. So they'll see like the ladder is 15 feet away from the wall. You are eventually going to need to plug 15 into this equation, but in order to do the related rates problem, you need variables, and in order to do because you need derivatives, and so you need to leave the variables in the equation until you take your chain rule, you do your related rates formula, get the rates in the problem, and then if you need to solve for X in terms of Y or vice versa, then go ahead and start plugging values in, but only plug them in after you've taken the derivative. You need that evaluated formula in order to get the derivatives that you need. So we're going to take the derivative, and if we take the derivative of X squared with respect to time, remember this is a chain rule, X is a function of time, and so we're going to take the derivative normally, and then we're going to multiply by dx dt. And then same thing for the y term. Y is a function of time. So we're going to take the derivative normally and get 2y, and then multiply by the chain rule, dy dt. And then the derivative of 25 is a constant. The latter is not changing. So the derivative of a constant is 0. And then we're given this dx dt. We're given this rate at which the ladder is moving away from the wall. What we want to find out is how fast is the top of the ladder moving down the wall. So dy dt is going to be moving in this direction. And so that's the value that we're looking for. So we're going to solve this equation for dy dt. And if we do that, we're going to get, let's see, if I move, let's do 2x dx dt is equal to minus 2y dy dt, and then divide by minus 2y, we're going to end up with, now the 2's are going to cancel, minus x over y dx dt is going to be equal to dy dt. So, okay, so now that we have our equation, now we can think about, okay, so what I need to evaluate this, I have dx dt in the problem. It's given as 1 meter per second. What I need to do is I need to find y. I have x. So I'm going to plug that into my equation. 15 squared plus y squared is equal to 25 squared. And if I take 625 and I subtract 225, which is what 15 squared is, I'm going to end up with y is equal to 20, because y squared is equal to 400. And then I have everything that I need. Dy dt is going to be equal to negative my x, 15 feet from the wall, divided by 20 feet up the wall, my y, and then dx dt was given as 1 meter per second. X is growing, so this is considered a positive 1 meter per second. And so if I evaluate this, notice that my y is negative because the y value is decreasing as the top of the ladder is coming down the wall. I end up with negative 0.75 meters per second. And of course, sometimes in textbooks, they will give you multiple values to evaluate. It's kind of a problem at. So in that case, you would then just find your new y value based on your alternate x value, and then you would repeat this. And you'll notice that the rate of change of y is going to differ. It's going to come down the wall at a different rate, depending on how far away the x position is from the wall. Because of that relationship, it has to be maintained here. All right, so that's our sort of easier example. And so the second example that I want to look at is involving a conical tank. And the thing to keep in mind about a conical tank is that there is a formula for the volume of a conical tank. It is 1/3 pi r squared h. And so it already has 3 variables in it, but we're only given the one rate of change. We're given the rate of change of the volume in this case. So we're going to have to find a relationship between r squared and h, so that, and that's fine. We can do that with a cone. But that's going to be necessary because we're only given sort of the height of the water at the time that we're interested in finding it. And so we're going to need, again, this relationship will sort of help us in a couple of ways. For one thing, it will eliminate this product rule that we would have to worry about. And it will also eliminate the need to have to find the value of both R and H at the position that we want to eventually evaluate this function at. So if we replace it with just R or just H, whichever one we're given in the problem, then we won't have to worry about having to solve for more variables than just the one. Okay, so our related rates problem is going to require us to, eventually we're going to need to find the derivative here. So before we do that, we need to come up with this relationship. And so we're going to draw a picture as we had in the previous example, but now we're going to look at the cone. So if I draw my cone, again, the problem says that the point is down, so this is our cone. And the other thing that we need to keep in mind about our cone is that in this particular problem, we have to be careful about the units that are being provided to us, because some of them are given in inches and some of them are given in feet. So we'll need to convert everything to the same unit. Now, this tank circular opening this way right here is given as 36 inches. Now, keep in mind, and then that means that the radius, since this is 36 all the way across, the radius is going to be 18 inches. Our relationships are going to depend on the radius because that's what's in the equation, not the diameter. It has a depth of 6 feet. So this height right here, that's 6 feet. But what is that in inches? Well, 6 feet times 12 inches per foot is 72 inches. And what we're going to need is we're going to need a similar triangle. Keep in mind, as we fill the tank tank maybe only goes to here, so we won't have the full radius across. But that ratio will be related to how high the depth of the tank is. So we need to come up with that relationship between these two. And so I'm going to draw another similar triangle here so that we can find the relationship between the radius and the height. Now, if we think about this relationship, remember this is a ratio for similar triangles. So I'm going to relate R over H. There's lots of different ways you can set this up, but R over H is equal to, what is the R in my original problem? It's 18 divided by H in my problem over here is 72. Oops. And then what we're going to do is we're going to come up with, we're going to replace R, because the problem is asking us how fast is the water rising when the water depth is 2 feet deep. So it's actually giving us information about the height. 2 feet is 24 inches, but it's giving us information about the height. And so what we want to do is we want to replace the R in our equation with an expression in terms of H. So if I rearrange this, R is going to be equal to 18 over 72 is going to reduce to 1/4 H. So if I keep these 18 over 74, that's 172, that's 1/4. Multiply by H, I get R by itself. And so what I can do is I can then rewrite my volume formula. It's 1/3 pi. R is 1/4 H squared times H. Which will simplify to 1/4 squared is 1 over 16. 16 times 3 is 1 over 48 pi. And then H squared times H is H cubed. And now I have a formula that has only 2 variables in it. And I'm given information about the volume is changing. This is inches cubed. So it doesn't even have to tell me how that it's volume, because the volume is implied with the cubic unit. And then we want to find how fast the height of the water is rising. So that's asking for dH dt. So let's take our derivatives. The derivative of V is dV dt. And then the pi over 48 doesn't change. We get multiplied by 3h squared, and then according to the chain rule, dh dt. And then we are given the 3 inches per minute. That's the dV dt. We plug that in. When the depth of the water is 2 feet deep, that's H, but remember we have to convert 2 feet to inches, so that will become 24. And so when we calculate this, we will get 3 inches cubed per minute. Is equal to pi over 48 times 3 times 24 squared, because 2 feet is 24 inches, and then dH dt. And we're going to need to obviously move everything over here. These 3's can cancel. And we're going to end up with dH dt is equal to, let's see, 24 squared. I believe it's 596, 576. So we move them over to the other side, we get 48 divided by pi times, let's be in the denominator, times 576 inches cubed per minute. And if we simplify that a little bit, we're going to end up with 1 over 12 pi cubic inches per minute. Which is very slow. 1 divided by 12 times pi is about 0.0265, roughly. cubic inches, or actually, this was cubic inches. The height is not increasing at cubic inches. Let's take my units in inches. Yes, inches. The height, the change in the height is increasing at inches per minute, not cubic inches. So at this point, when the height of the tank is 2 feet deep, the 3 cubic inches per minute is increasing the height of the tank very slowly. When it was further down and it's shallower and it's more narrow, you would expect that the height would be increasing more rapidly. But because the cone is getting wider as you get closer to the top, we can go back and look at our picture. The cone is getting wider as we get closer to the top. When we're 2 feet deep, we're already a third of the way full in terms of the height. And so the tank is starting to get wider. And at this rate, it'll keep filling, and eventually it will fill at the top. But the largest volume is going to be as it gets full. And so the height of the water will keep rising, but it will keep rising more and more slowly as it gets closer and closer to the top.